Good morning, guys. Before I start, any questions about yesterday's active class? Nope. Okay, guys. So let's just do this since we already discussed the topics, but there are some questions, and we can maybe just try to do them together so that you guys also get a little bit of clue earlier. Yes, okay. What kind of questions can be asked? Just so you guys are aware that, there's no class on Monday due to Martin Luther King Day, right?
Correct.
Good. Okay, guys. Okay, so just go to page 138. Okay, and these mainly are going to be questions of, as we can say, it's determining the focal depth. Okay. Now what they say is, it's a pair of 6 megahertz probes. So that mainly means that I have a pair. Okay, which mainly means a pair of 2. Okay, so we can just label them as as A and B. Okay. And although not directly mentioned, but indirectly it says that as a pair of 6 megahertz. So both of them have the same frequency. Yeah, okay. Okay, identical except from the active element diameter. Now please remember that yes, PCT was also known as the active element. Okay, so they had the same frequency, of 6 megahertz, but they're going to be different in terms of, the diameter of the active element or PCT. Now here we can say, one of them have an active element which has a diameter of 6 millimeters, and the other one has an active element diameter of 10 millimeters. Yeah, okay. The sound beam of which probe will have a shallower focus? Okay, so what they mainly are asking are which of these two, A or B, has a shallower focus. Okay. Now, what would that mean to have a shallower focus? You can rephrase that and say it's okay. Focus at a shallow depth. Or we can say it's okay, has a short focal length. Okay. So what we're actually looking for is going to be as okay, the lowest focal depth. Now we know that okay, as your focal depth or focal length is directly proportional to both of the factors here, which was frequency and diameter of the PCT. Okay. And what it is that we are looking for is the shortest. Now, since the frequencies are the same, well, okay, here in this case is okay, that's not going to affect your focal depth because had it been for the frequencies alone, well, okay, both of them would have had the same focal depth. But the other factor is the diameter of the PCT, which also was directly proportional. So here is okay, you can say it's okay, this here will have a greater focal depth or focus at a deeper depth. Okay, where this one here is okay, will have a shallower focal depth. So the one which had a 6 millimeter PCT would be the one with the shallower focal depth. Had they asked the other way and says, okay, which is going to focus at a greater depth or have a deeper focus, would have been this one. Did that make sense?
Yes.
Okay. Question number 2. Again, yes, okay, a pair of 9 millimeter, yes, okay, diameter probes. Again, yes, okay, we have probe A, we have probe B. Okay, now here is okay, what is the same is going to be, it's okay, the diameter of the PCT. So both of them is going to be as okay, 9 millimeters. Okay, so a pair of yes, okay, 9 millimeter probes are identical except from the frequency. So what's going to be, this is equal. The thing which is not going to be the same is going to be the frequency. Okay, which is respectively as okay, you can go and say as okay, 3 megahertz and 6 megahertz. Clear? Okay. Now again, yes, okay, which beam has the shallower focus? So they go again and say, yes, okay, shallower focus. Clear? Okay. Did that make sense? Okay. Which may or mean lesser focal depth over focal length. And we said, okay, focal length and focal depth was directly proportional to the diameter and the frequency. Now, since that's okay, frequency in both these here are the same. Okay, that's not going to affect or determine the focal depth when we compare the two. Or had it just been, yes, okay, the diameter of the PCC that would determine that is okay, they will both have had the same focal depth. Okay. But the frequency, okay, yes, okay, since we are looking at the least focal depth, and we know that, okay, yes, it's okay. Diameters. So the frequency, now since we said directly proportional, we're looking for the least focal depth. We may just going to choose the one with the shorter or a lower frequency. Did you guys get that?
Yes.
Good. Okay. Now let us just put it this way, guys, and say that you are given the same question here, but instead of asking us which has the lowest focal depth, but maybe it's just ask you then what is the diameter of the beam at the focal point. If the diameter, yes, question.
4.5 millimeters.
How many?
4.5 millimeters.
1.5 millimeters. Clear? Okay. Even if you are giving us the same question with the same data, and even if they have asked you which of these two here has the narrowest diameter at the focal point, it will be the same for both of them. Because our main determine that was the diameter of your PCT. Clear? Okay. So in this case, yes, both of them will have had the same diameter at the focal point. Where, yes, in the previous question 1, for instance, we had one PCT was 10 millimeter, one PCT was 6 millimeters. Right? Okay. Where we can mainly says, the diameter of the beam at the focus was going to be respectively as 5 millimeters and 3 millimeters. Did you guys get that?
Yes.
Okay, so please, if you got it, well and good. If you didn't, please ask, because this is going to become relevant in the next chapter. Mark my words. Okay. And what you see here is can be asked in a different way then. Okay. Question number 3. Now, which of the following probes has the beam with the deepest focus? Yeah, okay. Deepest focused, or what would that mean? Because that's the greatest focal depth, or what we can call as focal length. Yeah, okay. Now we know that yes, the focal depth was directly proportional to the diameter of PCT. And likewise, that's okay, was directly proportional to the frequency. So to find out, that's okay, the greatest focal depth, what do we need to do? We may as okay need to choose the transducer with the greatest diameter of PCT and the greatest frequency. That will give us the greatest focal depth. Okay. Now the first thing that they have given us is diameter of PCT. So we can say it's okay 4 millimeters, but then we have one which is 6 millimeters, so that's why okay 4 millimeters out of the race. We have another 6 millimeter, and then we have a 5 millimeter. So the 4 and 5 millimeters, yes, okay, they are out of the race. Now we just have to choose between B and C. Okay, where is going to be, okay, the next feature will be your frequency. So one is 8 megahertz. Let's see what the other one offers. Is 2 megahertz. So here is okay. What we have is this one is both the highest frequency and it's okay the greatest diameter. So B with a 6 millimeter PCT and a 8 megahertz frequency would be the transducer. Or it's okay, would be the transducer which had the greatest focal depth when it's okay comparing all these 4 transducers here. Did that make any sense?
Yes.
Good. Good. Okay. Now, question number 4 is mainly as okay, the same thing, but okay, as what they mainly just ask us is, okay, are the similar, yes, okay, type is going to, yes, okay, the shallowest focus. Okay, or it means, okay, well, yes, okay, the lowest or shortest focal depth or focal length. Clear? Okay. So since we are looking for the shortest, and we know that, okay, yes, is going to be directly proportional to both diameter and frequency. What we mean is, okay, you just need to choose as, okay, the one with the shortest or smallest diameter and the smallest frequency. So again, yes, okay, what do we have? We have a diameter of 4 millimeters. We have a diameter of 6 millimeters. We have a diameter of 4 millimeters, and we have a diameter of 5 millimeters. Okay, so in this case, yes, okay, this one here and this one here is out of the race because both 5 and 6 are greater than 4 millimeters. So we may, yes, okay, just have the A and C. Clear? Okay. Where now, okay, yes, okay. We just have to look for the lowest frequency as well. Which one these two here are the lowest frequency? So A has a frequency of 4 megahertz. And C, as in cat, has a frequency of 2 megahertz. So it will be transducer number C. Because of the smallest diameter, but same as here, but yes, okay, since this here is a lower frequency, then this here is a greater frequency. Okay. So lowest, shallowest focal depth. Yes. You got that?
Yeah.
Question 5. Now you can see it's the mainly as okay, the same concepts, just being asked in different ways. So it's okay, which of the following probe creates the beam with the shallowest focus? Again, it's okay. Lowest focal depth or focal length. Or which in question here is also yes, okay, the shallowest focus. Clear? Okay. Or if you don't like the word focus, yes, okay, they may, yes, okay, you can use yes, okay, focal point. Okay. So again, yes, okay, what do we need? What do we know? That, okay, yes, focal depth here is directly proportional to the diameter. Because that's okay, the diameter of the PCT. Clear, okay. And or we can say it's okay, the frequency of the transducer. Okay, guys, please, please, please make sure that you know that they are talking of the diameter of the PCT. And it's the diameter, not the thickness. Clear? Is that clear?
Yes.
The thickness of the PCT is okay, that will affect the frequency. Okay? Okay. So guys, this is diameter. This, if you look at it from the side, this will be the thickness. Whereas, okay, in terms of diameter for this kind of PCT is okay, this will be the height, and this will be the width. Okay, so the kind of PCT that we are looking at here, yes, okay, just look at a coin. That's pretty much okay what it looks like. Okay. Or you can compare it to. Now, what are we looking for? The smallest focus on the shallowest focal point, right? Okay, clear. Okay, shallowest focal point is going to mean, yes, okay, we call it going directly. So the smallest diameter and the lowest frequency. Clear? Okay. So when we say small diameter, large diameter, small diameter, large diameter, that's okay. When we say okay, we have a small diameter. So then we have a large diameter, then we have a small diameter, then we have a large diameter, A, B, C, D. Okay. Now, the large ones are out of the race. Because we are looking for the ones that had a small diameter. Okay. And now do you need to look for is okay, which of these two here, A and C, has the lowest frequency. Now A says high frequency, C as in cat says low frequency. So this one here with a small PCT and a low frequency will be the one with the shallowest focal point. Had it been the other way around, and they say it's okay, greatest focal point, then you go with large and large diameter, right? Okay. Here. Okay. And then just go with the, and I had to choose the one with the greatest frequency, which is, I guess, B. So B, sorry, B would have been the one that would have had the greatest or deepest focal point. Clear? Okay. Or the greatest focal depth or focal length. Did you guys get that?
Yep.
Next question. Now some true and false questions. Good. So we can say, okay, question number 6, which is, okay, yes, is this fellow here true or false? So what they mainly say is that the diameter or the active element's diameter and the near zone length are directly proportional. That's true. Now just look here, guys. They say that, okay, yes, the diameter of active element. Now, what do we call the active element? That was what we call the PCT. Okay. And what is the near zone length? Well, okay, guys, if you looked at the beam, this was your near zone. Okay. But when you measure, you can say, okay, when you measure the length of your near zone, that's okay. We can say the length of the near zone is what we actually can call the focal length or focal depth. Clear? Okay. Are directly related. So what is true to say that, okay, yes, for instance, we had a great PCT, we will have a great near zone length or a great focal length. Would that be true? Yes, guys. Is this true? The focal length is directly proportional to the diameter of PCT. Good morning. Would I be correct if I said that the diameter of a PCT is directly proportional to the focal depth? Students, what have we been talking about ever since this morning? Yes, students.
Yeah, they're directly related.
Okay, so that would be true of me to say that, right?
Yes.
Okay. Was it that hard to? Okay. Please don't go mute. Okay. I know yesterday is okay. We were freezing a lot, but okay. It Now, if I, for instance, say that, okay, yes, if you didn't say diameter, if you but said thickness of PCT, is that directly related to your focal depth on near zone length? Yes, students. Anybody want to answer this one?
Could you say that one more time?
If the question read true or false, the thickness of the active element and the near zone length are directly related. Would that be true or false?
That would be false.
That would be false. Very good. Clear? Okay. Now, which value you say is okay? Oh, okay. Because it's not the thickness, but the diameter. But here it says, okay, greater thickness. Greater thickness would be a lower frequency, and a lower frequency will mean a lower focal depth. Which way you took it. Clear? Question number 7. And again, yes, okay, true or false. So it's correct to say that, okay, yes, that the frequency of the transducer. And again, yes, okay, your near zone length. That these two here, okay, are inversely proportional. Yeah, guys, that's false. And again, yes, okay. And we say it's okay. If this here is okay, was your near zone. Right, okay. Or your transducer. Clear, okay. But is that near zone, or that actually, okay, becomes this distance, yes, okay, become your near zone length, which becomes your focal length. Yeah, okay. So this focal length or focal depth here, is that going to be as okay inversely proportional to your frequency? No, because we said that, okay, yes, focal length or depth was directly proportional to frequency. So that makes it falsus. Did you guys get that?
Yes.
Good. Question number 8. Now again, yes, okay, true or false. Now what they say here is wavelength. Is that inversely proportional to the, okay, not frequency, so this. Is that inversely proportional to the near zone length that is true. Now again, yes, okay, we just look at it, we say yes, okay. This is our transducer or PCT. This here was your near zone. Right, okay, at which it ends up at a focal point. Yeah, okay, where we say, okay, now this length here of your near zone becomes your focal length. Now we know that, okay, as this focal length or focal depth, as you call it, was directly proportional to, yes, okay, the diameter of PCT and diameter of, I'm sorry, not diameter, frequency of transducer. And some of you are going to say, but yes, okay, in this equation, does it talk about wavelength? Maybe not directly, but indirectly it does. So maybe, yes, okay, you can say, for instance, that if you had a greater frequency, you would have had a greater wavelength or greater, sorry, focal depth or focal zone. Not focal, not focal depth or focal length. A greater near zone length. But what does this greater frequency mean? That you have a really shorter wavelength. Okay. So in that instance, okay, with a greater frequency, you have a lower wavelength, and with a lower wavelength, you have a greater focal zone. So yes, okay, this is great, this is low. That would mainly mean that, okay, yes, these two here are inversely proportional. Did that make sense? Okay. The answer would still had been false had it even said yes, okay, period. Because we also know that, okay, period, well, okay, it is just, okay, directly proportional to wavelength, and or it's inversely proportional to frequency. So even if we talk about, okay, the relationship between frequency, that's our period, and the near zone length, they would also have been inversely proportional. Did you guys get that?
Yes.
Okay. Now some of you would say, well, okay, that is not in chapter 9. Well, that's what we already have learned. Clear? Okay. So don't unlearn what you already have learned. If you tend to forget about it, well, that's okay, just evaporates off your cerebral cortex. My advice would be that from time to time, go back and that's okay, just refresh your old chapters. Okay. Any questions? So these are the kind of questions that you may, as okay, come across. These kind of questions. But just because here give wavelength, can I give you the same question just by, yes, okay, changing the wavelength by period? Yes. Have we talked about it? Yes, we just did, right? Okay. Any questions about the focal depth and its relationships? And now you can say, yes, okay, focal depth or focal length can also be known as the near zone length or near zone depth, right? Okay. Good. What happened? Okay. What happens to the beam in the near zone? Yes, students, what happens to the beam in the near zone?
Converges.
Converges. Okay. How else can we phrase the word converges?
Narrows.
Narrows. Good. How else? Narrows. Okay, converges. How else?
Could you say decreases in diameter?
Exactly, decrease in diameter, right? Did that make sense? Good. Now, please keep in mind, guys, that decrease in diameter happens both like this and like this. Yeah, okay. Likewise, that's okay in the far zone. The divergence happen both like this and like this. Did you guys get that? Good. Now let's just look at the questions on page 141. Page 141, sorry. And what do we have? Yes, okay, we have question 1. So what do we have here? Yes, okay, a pair of probes or pair of 6 megahertz probes are identical except from the active element diameter. So again, we can say, okay, we have probe A and we have probe B. And okay, yes, their frequencies are the same, 6 megahertz. Yeah, okay. Or we can say, okay, they are identical except from the diameters of the active elements. So PCT diameters, which is respectively, it's okay, 6 millimeters and 10 millimeters. Now, which beam will be more compact in the far field? Now here it's okay, they mainly play a little around with the words. But let's just say, okay, what do we mean by a more compact beam in the far field? So these questions here, I mean, that's okay about, it's okay, what we call beam divergence. Clear, okay? Now more compact in far field or far zone. Now what they mean by more compact is going to be less divergence. So that's okay, of these two waves here, this one here is going to be more compact, where we can say, it's okay, this one here is going to be less compact. Of course, it's okay in the far zone. Did that make sense?
Yeah.
Yep.
So more compact a beam is, yes, okay, in the far zone, yes, okay, it's going to, yes, okay, diverge less. Okay. Now, when we say, yes, okay, more compact, that's going to be, yes, okay, less divergence. Okay, now what do we, yes, okay, we are looking for less divergence. Now we know that divergence of beam is inversely proportional to both frequency and the PCT diameter. Okay, now here is okay, the frequency is okay will not be is okay playing a decisive role because they both are of the same frequencies. So the parameter that we need to look at is going to be as okay, the diameter of the PCT. Now, since we're looking for least divergence, okay, and we know that, okay, yes, that divergence is inversely proportional to the diameter. We actually, it's okay, have to look for the greatest diameter. So it's going to be the one with a 10 millimeter PCT. Did you guys get that?
Yep.
Good. Okay. Now, if you just say it's okay, what will be is okay, the diameter of the beam at the focus. This one here will be 3 millimeters. This one here would be 5 millimeters, but now having the diameter of the beam at the focus. Just good. Question number 2. Okay, again, yes, okay, a pair of 9 millimeter probe, 9 millimeter diameter probes. Again, yes, okay, a probe. So we can say, okay, we have probe 1 and 2. And the diameters of the probes is 9 millimeters. Good. Except from the frequencies of 3 and 6 megahertz. Yeah, okay. So what are they asking? Yes, okay. Which of these, which sound band will spread out more in the far field? So yes, okay, we can say, okay, have a greater spread out, which means, okay, we say, okay, we'll have a greater beam divergence. But we already know that, okay, yes, this beam divergence in far zone is like, it's of course, it's okay, it is inversely proportional to the diameter, it is inversely proportional to the frequency of the transducer. Did you guys get that? Okay, so what do we say? That, okay, yes. Now, since yes, okay, the diameter is the same for both of them, that's not going to, yes, okay, be what we are looking for. Now, since we are looking for a greater beam divergence, which is inversely proportional to frequency, it will be the one with the lower frequency, which has greater beam divergence. Whereas the one with a higher frequency is going to have, okay, yes, the lesser beam divergence. Did you guys get that?
Yeah.
Good. Question 3. So which of the following probes create the least beam divergence, or creates a beam with the least divergence? Okay. So again, yes, okay. Least divergence. Okay. In the far field, which we know is okay as inversely proportional to the diameter and inversely proportional to the frequency. Now, since here is okay, they're asking about the least, we had to look for the one with the greatest diameter and greatest frequency. Clear? Okay. Now, what do we have as options? We have 4 millimeters. Again, yes, okay, we have 6 millimeters, we have 6 millimeters, and we have 4 millimeters. So directly, yes, okay, yes, okay. B and C, yes, okay, are out of the race because they are great diameter transducers, okay? There, I guess, it's 5, sorry. And then we can say, okay, 5 is greater than 4, so that's also out of the race. What the hell? OMG. Is the 6 millimeters because we are looking for less divergence, so greater diameter. Okay. So this and this here is okay are out of the race, and okay, yes, these here are in because they are greater diameters. And then we just have to look at the one with the greater frequency. Where okay, yes, B is 8 megahertz and C is 2 megahertz. Clear? Okay. So greater diameter, greater frequency, lesser divergence. Whereas, okay, so on the other hand, we could have said lesser diameter, and then of course, yes, okay, what was the frequency? Yes, okay. 4 megahertz, that would have been the greatest divergence. Did you guys get that?
Yep.
Yep.
Okay, okay. Question number 4. Now, which of the following probes creates a beam with the most divergence? So greatest divergence. And when we mean it's not going to know that, okay, it's inversely proportional to the diameter and inversely proportional to the frequency. Now, when we look for the greatest, it will be the least and the least. One of the first options that we have is 4 millimeters, then we have 6 millimeters, then we have 4 millimeters, and then we have 5 millimeters. So the smallest diameter that we have here is 4 millimeters. So 6 and 5 are out of the race. So now we mean is okay, just left with A and C. B and D are out. Now just lowest frequency, what do we have in A? Is 4 megahertz. And C is 2 megahertz. So C as in cat, because of a 4 megahertz frequency or diameter. And 2 megahertz frequency is the lowest of them all, which is going to have the greatest divergence. Or greatest divergence, or you can say it's okay, least compact. Did that make sense?
Yes.
Good, but question number 5. Now, which of the following probes creates a beam with the most divergence? Now we know that divergence is inversely proportional to or diameter and inversely proportional to the frequency in our gain. Since we are looking for the greatest, it will be the smallest and lowest. So what options do we have? We have small, we have large. Again, it's okay, we have small and we have large. Where the large ones are out of the race. Where we just have to choose between the two small ones. And okay, mean that's okay, look for the low frequency. So here we have a high frequency, here we have a low frequency. That would be the one with the least divergence. Okay, or the greatest divergence, sorry. Any questions? Now, next question is question number 6. And true or false. And is it true to say that, okay, yes, the transducer's frequency is and beam divergence are inversely proportional to one another? That's true. Because we know that, okay, yes, the greater the frequency, less divergence. Or lower frequency, greater divergence. So that makes these two factors here inversely proportional to one another. Did that make sense?
Yes.
Good. Question number 7. Again, yes, okay, they ask true and false. And is it true to say that the active element's diameter is inversely proportional to the beam divergence? That is true as well. Because what we know is that, okay, yes, if we have a great active element in diameter, that's going to mean a low beam divergence. Or if we have a small active element diameter, that's going to mean a great beam divergence. Is that clear?
Yep.
Good. No, although not written in the book, but okay, there's nothing that say that I can't make up my own question. And my question is going to be true and false here, and I will say it's okay. Is it true or false to say that period of a sound wave is directly related to the beam divergence?
That's true.
That's true, right? Because what we can say is, okay, if we have a greater period, we will have a lower frequency. And a lower frequency will have a greater beam divergence. So this and this. Arrow up mean that, okay, these two fellows here are directly related. Good question. You sound prepared for this chapter 2. I'm not going to play those games. Okay.
Can you do a few more like that?
Okay. What do you mean?
Just like a few more examples.
Okay, let me just. Okay. Oh, I can always make up crazy shit.
All right.
So can we say it's okay? A question, and then we can say it's okay, any true or false. I just like true and false questions. So is the focal depth inversely proportional to PRP? Would it be true to say that your focal depth is inversely proportional to the pulse repetition period? Yes, guys. is focal depth inversely proportional to process repetition period. Yes, Caitlin, what do you have to say?
Is that false?
It's false. Why?
Wouldn't it be
Um,
directly related? Or I'm not sure.
hmm.
I'm struggling with this one a
Okay,
lot.
why do you think it's directly related?
Well, I don't know. I just think depth is directly related to PRP. But this is
Well,
focal.
depth is something else, and focal depth is something
Yeah.
else, my dear.
So are they unrelated?
Unrelated, that's what makes it false, okay? Okay. So even if I say, yes, okay, PRF, they will be unrelated. You guys get that. So it's a matter of, okay, as do they have a relationship and all that makes it false. Because they happen to be unrelated. Good.
Mike, so far, like PRP and PRF like aren't really related to anything in the like past few chapters, right? Like, is there anything you can think of that they are?
Depth,
Yeah, but that was in their like
go and return time,
okay.
time of
Yeah.
flight.
Okay, yeah, that makes sense.
Yeah, okay. As a matter of fact, yes, okay, chapter 4, or that last part of chapter 4 that talked about pulse repetition period and pulse repetition depth, frequency, sorry. In relation to depth was just because it's okay, further elaborated in chapter number 7. Okay, where still yes, okay, the old the same old relationship that a okay, pulse repetition period is directly proportional to your depth of image. Okay, or as okay, what we may say is okay, a depth of a reflector, but peace be with that. Okay, but okay, and inversely proportional to your PRF. Yeah, okay,
Got it. Thank you.
no problem. But my dear, listen. Okay, that's going to get handy because you can say you may have a, let's say it's okay that you have, we can say it's okay, 2 images. Comparing 2 images here. And you say it's okay. Here's okay, the depth of our image is 5 centimeters. Here we may say it's okay, just 10 centimeters. Okay, so that's the depth of your image. But here, yes, okay, you'll still be able to, let's say it's okay, focus at 3 centimeters, and even here is okay, you'll be able to focus at 3 centimeters. Well, since you here have kept the depth of your image limited to 5 centimeters, you will not be able to focus at 7 centimeters. That's going to be impossible. Okay, here you can, yes, okay, focus at 7 centimeters. But that's going to be a focal depth. These or this here is okay, that'll be a focal depth. Did that make sense? And what did we mean by focal depth? The depth at which the beam is at its narrowest. Clear? That's what your focal depth means. Okay. So the depth within your image at which the beam is at its narrowest. Because if you keep your image depth at 5 centimeters, you can't focus at 7 centimeters or 6 centimeters. Because anything beyond 5 centimeters is not in your image. Did that make sense? So if you want to focus on something, let's say it's okay at 6 centimeters, well, you have to increase the depth at least of your image at least to 6 centimeters, and then you can focus on 6 centimeters. Clear? Did you get that, my dear?
Yep.
Okay, good. Okay, guys. Should we look at spherical waves? Now, before we get into all this, well, not all this, it's because made is okay, just a theoretical point that we just have to get cleared. Okay. Now, what I said earlier, I said it yesterday, I even it's okay, repeated earlier today. Then when we say it's okay, convergence of the beam, convergence of the beam, how did that happen? Both like this and like this, right? So the convergence or narrowing of the beam happens both in the horizontal plane and the vertical plane, which may mean that, okay, as from side to side it becomes narrow, and from top to bottom it becomes narrower. Did that make sense? Clear? Okay. Now, likewise, okay, it gets to its narrowest point. And what happens, what we call the focal depth or the focal point, sorry. Okay. And what happens to the beam after that? It diverges. Clear? Okay. But we can say, okay, what's going to be the form of divergence? Well, okay, it's going to diverge on the horizontal plane and on the vertical plane as well. Did you guys get that? Yeah, okay. So what they mainly say is that, okay, yes, the beam shape is the same as the shape of an hourglass. Have you guys seen an hourglass?
Yes.
Get clear? Well, it's okay, it doesn't really matter. It's okay. We can say, okay, here, if you look from the side of the hourglass, it's okay. It has the shape. Whereas, okay, yes, if we look at it from another side, it's okay, well, how? That's okay. Somehow similar shape. The remaining can say, okay, and all this point here is okay, is the focus. Did that make sense? Now we can even say here that, okay, yes, we had one PCG. Clear, okay. Now, what they mainly say is, okay, what the whole concept mainly is that, okay, this PCG here actually is, okay, is, we can say it's okay, divided into small pieces. But mainly can says, okay, it's going to be each piece of the PCG that will produce their own waves. And these waves here are going to be, that's okay, what we can call spherical waves. Did that make sense? These spherical waves, we can also call them wavelets. Now, wavelets mainly as okay just means short waves. Oh, sorry, small waves. Clear? Okay. Okay. And they can also be called fusion wavelets, or simply as okay, just fusions. Did that make sense? And why do we call them fusions or fusion wavelets? It's mainly as okay because okay, what these wavelets here are going to be doing is, because what you actually say is okay, now each of these here, we can say it's okay, or each of these wavelets, we can put this way. Each wavelet that we just happen to call a fusion or a fusion's wavelet or spherical wave actually are going to be as okay individual sound waves. Did you guys get that? So what is that we now have? This was our PCG. And it produces a lot of these fusion wave as spherical waves or wavelets, where we can say, okay, each of these is going to be as okay an individual sound wave. We actually have multiple. Forget about multipliers, okay, we have two or more than two sound waves. That we call fusions or fusion wavelets, right? Did you guys get that?
Yeah.
Okay. And of course, Christian, we know it because that's okay. What we call is okay the Huygens principle. It's something that okay, as a scientist came up with, which is the name was Christian Huygens. Or what he mainly is okay, mainly said okay, these Huygens or Huygens wavelets, since that's okay, they are individual sound waves. Now, what do you have? Two or more than two sound waves. And what happens if two or more than two sound waves travel in a medium?
Interference.
They interfere. Now, what are the forms of interference?
Constructive and destructive, or
Constructive and destructive. Clear? Okay. So, what we mainly can say is that, okay, yes, due to, yes, okay, the interference, which would be, yes, okay, constructive interference, or, yes, okay, destructive interference between the wavelets. That's going to be how your sound beam attains this hourglass appearance. Did you guys get that? Okay, so although it's okay if we just look at it and say it's okay, well, this for instance, okay, here, this becomes just okay, our hourglass appearance. You can say, okay, let's say it's okay, just sorry. Let's say it's okay, the near zone. Okay, where we have all these wavelets, but we also have wavelets are here, for instance, okay, and here. Okay, but what we mainly can say is okay that these here are the wavelets that we found, and let's say it's okay, this region here, or let's say it's okay, this area here is okay, are going to be as okay destructively interfering with one another. Whereas we can say it's okay, these wavelets here, for instance, are going to yes, okay, constructively interfere. But your Huygens principle mainly say that okay, as these multiple Huygens or Huygens wavelets, yes, okay, will interfere, which can be either destructive interference or it can be constructive interference. And as a result of that, that is how, yes, okay, our beam gets that hourglass appearance. If that makes sense. So had it not been for, yes, okay, this Huygens principle being brought up in this chapter here, we probably, yes, okay, wouldn't have been talking about interference back in chapter 2. Yeah, okay. So what is going to, okay, you see it comes up in the questions here. But the Huygens principle deals with what? Interference. Interference of what? What we call spherical wavelets. We can also simply call them wavelets. We can call them Huygens, we can call them Huygen wavelets or diffraction wavelets. These are all the names that these small waves here, yes, okay, go under. Little thing, a lot of names. Clear? Okay. So Huygens principle may say that, okay, these wavelets here interfere. Now, when you have constructive interference, what would be the result of constructive interference?
A bigger final wave.
Exactly. Caitlin, can you rephrase the word have a bigger final wave?
The final wave would be greater than the initial waves.
Okay, can you still rephrase it?
Um,
What would you, okay, how would you rephrase the word bigger wave? Anybody want to help her?
Greater amplitude.
Greater amplitude. Did that make sense? So would it be far, would it be correct to say that, okay, yes, constructive interference is okay, produces waves of greater amplitudes? No. It would be correct to say that, right? Okay. Where destructive is just going to be the other way around. That your final wave is smaller than either of the components of the waves that we've talked about in chapter 2, but here we just rephrase that waves into wavelets or Huygens or spherical waves. Did you guys get that? Now, what does Snell wave or what does Snell's law deal with? Not Snail, but Snell's.
refraction.
Refraction, exactly. It's dear students, as far as the theory is concerned, this was all that I could offer for chapter number 9. Let me just see. No, we got 9 questions here at the end of the chapter. Now, what do we have? We probably going to let's see. Try to find something. Yes. I think it's U4. Oh yeah. So even in the back of the book. Yeah, okay, so we got 9 questions, that's okay, at the end of the chapter. I think most of these are okay about sound beams, but then we have just okay some questions in the chapter review as well. Okay, so from question 304 to 327, which goes from page 487 all the way to 491. Okay. Now just check. Well, okay, yes, you can say it's okay. 10 minutes of your regular break. And let me give you guys, okay, half an hour extra to try to just, okay, answer as many of these questions here as you can. And when we come back, yes, okay, we can start looking at them, okay? And play our little dirty games. Okay? So I see you guys around, should we say 11:15-ish? Is that fair? Okay. Have fun then. Hey guys, welcome back. Okay. So did you guys have fun? Okay. Let's just see. Okay, Christian. That's fine.
It's good.
Yeah, okay, thank you.
Thank you.
No problem. We may even finish before that, so. So where were we? Good. So we can say page 143, question number 1. Now the frequency of a transducer does not change. So frequency is equal to its okay frequency. Yeah. If the diameter of a new piezoelectrical material increases, so we can say, okay, PCT diameter increases. Okay, what happens to the near zone length? Now, when this goes up, then the near zone length, as I say, what means okay, just the length of your near zone, which is the focal length, increases. Did that make sense? Because these are directly proportional to one another. But we kept the frequency the same, but if we increase the diameter of the PCT, okay, it means it's okay only as possible. It's okay if we say it's okay that we use a different transducer. Okay, that, okay, as the focal length or focal depth will increase. Did that make sense? So it's all about, yes, okay, you can say the relationships. Now, question 2. Okay, yes, okay, the frequency of a transducer does not change. So the same concept here says, okay, that the frequency remains the same. Clear? Okay, if the diameter of the new piezoelectrical crystal increases, so it's okay, we can say, okay, the PCT diameter, if that increases. Okay, what happens to the beam diameter in the far zone? In the far zone. Okay. Now what remaining can say is, okay, was the change in beam diameter in far zone was what we call divergence. Yeah, okay. The remaining say that, okay, yes, beam divergence was inversely proportional to both the PCT diameter, but that stays the same. Oh, sorry. Sorry. The frequency, sorry, for instance, first, which is the same. But the PCT diameter increases. That's going to mean that there will be a lesser beam divergence in the far zone. Clear? Because lesser divergence means that there will be a lesser change in the beam in the diameter of in the far zone. Did that make sense?
Yes.
Okay, so here they really are playing around with the words. Clear? Okay, we can also say, okay, this lesser convergence, or sorry, lesser divergence, sorry, mainly mean that, okay, as the beam is more compact in the far zone. Whichever way. Did you guys get that?
Yep.
Okay. Question number 3. The frequency of a transducer does not change. Okay. Because the frequency equals frequency remains the same, right? Okay. Okay. Now, if the diameter of a new piezoelectric material increases, what happens to the wavelength? Now, if the diameter of PCT, that there's an increase in the diameter of the PCT. If that increases, the question is, okay, what's going to be the effect on the wavelength? Nothing. Did that make sense? Right, okay. Okay. Now had it said thickness instead of diameter. Then okay, if you increase the thickness, then okay, yes, of course it will affect the wavelength. Okay. Then your wavelength will also increase. Okay, but here they play around with, okay, as you paying attention, because okay, the frequency remains the same. If we said that the frequency hadn't changed, it has increased, for instance, then okay, let's say that the frequency was not the same, but the diameter either increased or decreased, or as I say, it's okay, it's okay, to keep it the same, then your wavelength had decreased. Clear? So that's okay. That says okay, the wording of the questions. Okay. And maybe not yet. Maybe not yet, so at least so far, none of you have said so. But it's okay. There are some questions where the wording may be a little confusing. That you may have to read it 2 times or 3 times to actually figure out what the is it that who wrote the questions here is okay, essay. Is that clear? Okay. So have you come across a question like that so far? That you have to read it 2, 3 times first? Somebody is silently nodding. Okay. But it's all just a word. I mean, now, guys, that's just an easy tip. It may, it's okay, be a little bit time consuming, but it's okay. If you keep on doing it, it becomes just, you can practice makes perfect, right? Okay. If you read a question where you don't really figure out or are able to figure out the wording, change the words out. Okay, but don't change the words out in a way that, okay, yes, at the end of you replacing the terms or words in the question is okay, you end up with something which means something completely different. God, then you're going to, yes, okay, choose the wrong answer. Okay. But you, yes, okay, though, yes, okay, change the wording, but if it still means the same, that's okay, it's going to be, yes, okay, the same question, just phrased in a different way that makes more sense to you. Okay. So that's okay, it's always easy, it's okay, just to do something like this. But of course, that's okay, again, you still have to have, okay, as a solid grip on your relationships. Question number 4. Now, the frequency of the transducer does not change. So again, or frequency is okay, remains the same. If the diameter of a new piezoelectrical crystal increases, what happens to the diameter in the near zone? So that's okay, the diameter of the PCT is increased. What's going to happen to the diameter of the beam in the near zone? Now just look at it in this way. Let's say, okay, as we said that we had, let's say it's okay, 5 centimeter PCT, and we have a 2.5 centimeter PCT. Clear? Okay. Now here it's okay, they're not asking us, okay, what happens to the focal depth or something like that, the diameter. Which is mainly that's okay, and what they talk about is mainly it's okay, what's going to be the diameter here versus diameter here. Did that make sense? So that's okay. What you mainly will say is okay here is that okay, you have a greater diameter, which is here. Okay. Whereas okay, you have a smaller diameter, which is here. Okay, when you increase the diameter of the piece, yes, okay, you're going to have a beam with a greater diameter. Okay, we then just know that okay, as this beam here is okay, since it's the same frequency as okay, well, focus at a shallower depth, whereas okay here, this beam here is okay, will focus at a greater depth because of the same frequencies. But meaning is that okay, what the frequencies I mean or cause is that since they are the same, they're going to be as okay an equal degree of convergence of the beam. But since you start smaller, okay, that's going to cause okay the beam will reach to a focal point at a narrower distance, okay, at its narrowest point at a shallower distance. Did that make sense?
Yeah.
Okay. Or even if you don't want to go to that extreme, you can just say, okay, well, okay, we know. But prime, that's okay. What they just asked is that's okay. If you increase the diameter of the piece, what's going to be its effect on the beam? Yeah, right at the start. And of course, that will increase. Question number 5. At what location does the beam diameter? Okay. At what location is the sound beam's diameter 3 times greater than the transducer's diameter? Now, although it's okay, they say transducer's diameter, but what they actually is okay mean is of that single PCT. Okay. Now, although they haven't given us, okay, although they haven't given us a number, but let's just, okay, as for our own sake, say that, okay, here, let's say that, okay, as our PCT's diameter is 5 millimeters. Did that make sense?
Yep.
Yes.
So the question they mainly ask is, at what location of the sound beam? Okay, where mainly can say, okay, this here is going to be as okay, our sound beam. At which point in this sound beam here is it that the diameter of the beam is going to be equal to what is 3 times that of the transducer. which we in this instance, like we say, okay, 5 millimeters, that's a number that we took ourselves, okay. Would be 15 millimeters. Now, guys, what we know here is that at the focal depth, what's going to happen? The diameter of the beam is going to become half, which is 2.5 millimeters. Did you guys get that?
Yes.
Good. Let us just assume that, okay, this focal depth here, focal length here is 4 centimeters. So what you mean is, okay, if you check, you can say it's okay, another 4 centimeters. What's going to be the diameter of the beam here? It's going to be back at 5 centimeters, right? Or 5 millimeters. Now, for instance, okay, if we take another 4 centimeters. At this case, yes, okay, the beam diameter is going to be 10 millimeters. And again, yes, okay, we can say, okay, we take another 4 centimeters. Then the beam is going to be 15 millimeters. Clear? Okay. Did that make sense?
Yeah.
Okay. But they mainly says, okay, at what depth is it that the diameter of the beam is going to be 3 times greater than the diameter of the PCT? And that's going to be as okay at a depth which is equal to 4 focal depths, which was 4 centimeters, 4 centimeters, 4 centimeters, 4 centimeters. So how many focal depths did we have? Or how many distances of focal depth did we have? A total of 4. Did that make sense?
Yes.
So had we, for instance, okay, said 2 times greater than then there would be at a depth of 3 focal depths. Clear? Okay. Where Harry said, yes, okay, not 2, not 3, but had been equal to the distance of the piece, okay, size of your PCT. That would have been at a distance of 2 focal depths. Did you guys get that? Okay. Now, this is one of those questions that the students repeatedly keep on asking me about. Okay. Now to talk about, yes, okay, the first questions of, okay, yes, that we did yesterday. Okay. But, yes. So a question is, okay, where you actually, yes, okay, weren't given any numbers, But you can say, okay, the way to simplify, you can put any size of the PCT. 5 is not a standard number. Clear? Okay. 4 doesn't have to be the focal depth. You can switch them around. It doesn't really matter. Clear? Okay. But that's how you mainly as okay get the words out of the question as okay mainly says okay what in the blue is it that he was asking about. Okay. Did that make sense?
Yeah.
Yep.
Good. Any questions?
Not yet.
Not yet.
Mike, you said something about 2 depths. Like if it was,
If it has said twice the size of the PCT.
oh, okay. All right, thank you.
That's going to be twice the size. So then you can make say, okay, what is going to be 10 or 2 times 5? Now I've been 10 millimeters. Where do you have diameter of the beam at 10 millimeters? At 1, 2, 3 focal depths, right?
Yep.
Yeah. Okay. Where do you have that? Okay, that they're equal at a distance of 8 centimeter, which is twice your focal depth. So I thought here going to be 2 focal depths. Well, okay, what depth do you have that is going to be? It's okay, half. That's going to be okay at the focal point. Did you get that?
Yeah, I mainly just needed the when they're equal. So that's helpful. Thank you.
Okay, no problem. Question number 6. Now, what is the shape of a sound beam created by a small piece of PCT? Small piece of PCT is made as okay, going to create as okay, what we call the wavelet, or what we call the fusion, or what we also is okay call the Huygens wavelet, or what we also call is okay a spherical wavelet. And what they say is that they are V-shaped. Is that clear? And that's why we also can call this okay, all these is okay, they can also be called as okay, V wavelets. Question number 7. Now, which of the following explains why it's okay, sound being created by a disc-shaped PCT have an hourglass appearance? Okay. Now you may see as okay, Bernoulli's principle written here, and you may be as okay scratching your head and say, what the is that? We will talk about Bernoulli's principle in a later chapter. Okay, but that has nothing to do with the shape of the beam. Sheffield's law, well, okay, I may know a lot of things, but I don't know, okay, Sheffield's law. Okay, please be with that. Ohm's law, well, okay, again, you come across that in chapter 18. All this, okay, don't really know why they had to mention this law here because it's irrelevant in that case. So the only one here that explains is, okay, why the beam held this hourglass appearance is the Huygens principle. Now, which of the following location is deepest? Now, which other way you want to look at? You can say, okay, if this is an image. Or you can say, okay, if you say, okay, this will say, okay, was a transducer with the PCT, in which is, okay, we have a beam, for instance, right? Now, the end of the Fresnel zone. End of Fresnel zone. Now, this here is your Fresnel zone. So the end of that is going to be here. Yep. And let's just say that, okay, yes, if this here is this, okay, let's just keep the colors the same. This point here is okay, was our focus. Then this would be as okay, where our Fresnel zone ended. Beginning of the focal zone. Now this here is okay, was our focal zone. Then this would be the beginning of the focal zone, which would be here. And it's okay, what they asked us about is okay, which of these points here is going to be the deepest? So you can already, it's okay, check that one out. Focal depth. Well, guys, this is going to be the focal depth as well. Because, okay, the depth of focus. And beginning of Fraunhofer zone. Oh, okay, sorry, I mixed them up. And the okay, and the focal zone. Okay, so now we're looking at the one below. So, and the focal zone. So this is going to be okay. You end the focal zone here. Sorry. Yeah, okay, and the Fraunhofer zone. Okay, this is going to be considered okay. End of Fraunhofer zone. Okay, and end of near zone. Even this here is going to be okay. End of the near zone. So the one that is going to be deepest is going to be okay. End of the Fraunhofer zone. Okay. Did you get that?
Yes.
Let's see. We can say last question is going to be question number 9. Now, which of the following location is most shallow? So again, yes, okay. We can take an image. And already likewise, it's okay. We can take a transducer with a PCT. And yes, okay, beam. Or what we may have been asked here about is going to, okay, so which location here is going to be the shallowest? Beginning of far zone. Now, beginning of far zone is this part here. Yeah, okay. So that becomes just, okay, your focus. But that's also going to be, it's okay, the beginning of your far zone. Beginning of focal zone. Now we can say, okay, if this here is, okay, was your focal zone. This here is, okay, was your focal zone. Beginning of the focal zone is, okay, that will be here. Okay. The focal depth. Now again, yes, okay, the focal depth is at the depth of the focus, which is the focus. Yeah, okay. And beginning of Fraunhofer zone. Which is just the same as option A, which was the beginning of the far zone. So here's, okay, the point that is the shallowest is the beginning of the focal zone, because it falls, it's meaning as, okay, a point within the near zone. That's which other option we had, whether that was, okay, beginning of the far zone, whether it was the depth or focal depth, or whether it was the beginning of the Fraunhofer zone, all refer to the focus or focal point. Did you guys get that?
Yes.
Okay. Are you guys good? Good. So can we go on? Can we go on to the questions in the back? Okay. Did any of you try to look at those? Or you didn't have enough time?
Had enough time.
Okay. So you finished all of them, Kathleen?
Yes.
Okay. Were you able to answer them correct?
I struggled with some of them, but
Okay. Let's see.
all right.
Well, if your blood glucose level gets down, just let me know. I'll keep a chocolate bar or candy, something handy. Okay, guys, so our questions is going to be, are we going to go on to page 487? And it's going to start at question number 304. So what is the region from the transducer to the smallest cross-sectional area of the beam called? Which mainly says, okay, what do we call? No, that says, okay, this here is, okay, is our beam. Okay, and what the mainly says, okay, what do we call the region from the transducer to the area where the beam has the shortest cross-sectional area? Which means it's okay, just going to mean it's okay, the smallest diameter. What do we call this region here? Now, this is known as the near zone. We can also say it's okay, it was called the Fresnel zone, or it was called the near field, right? Did that make sense?
Yes.
Okay. So be watchful, because that's okay. They're not asking about what do we call this area here. If that has been what they asked, then the question would have been is, okay, what do we call the region of the beam where it has the lowest cross-sectional area or cross-sectional diameter? Then your option would have been A, which is focus. Half value layer thickness, well, okay, not relevant here. Near zone, that's what we call this area here. Okay, now please keep in mind, as okay, you could be given the same question, but the option may be Fresnel zone or near field. And far Hofner zone, that's mainly it's okay, what we call, what we have after that point. Did that make sense?
Yes.
Yeah.
Okay. Question number 305. Now the area that starts from the beam's smallest diameter and extends deeper is, so again, okay, so we have a beam. So what they say is, what do we call the area that starts from the beam's smallest diameter? And where, okay, starts from the beam's smallest diameter. So starts here. Okay, and extends deeper. What do we call this area here? Here's the far zone. Here, okay, or what we also call the Fraunhofer zone. Clear? Okay. Have you heard the word distance zone anywhere? Have you heard that term anywhere? Distant zone? No.
Is that the same thing as far zone?
Far zone is Fraunhofer zone or far field. Okay. Okay. But again, you can say it's okay. If you don't know that far zone was called Fraunhofer zone, then okay, yes, you might have been lost. Question 306. So guys, please, when I say it's okay, that thing that goes under multiple names, you have to remember those names. Now, which of these terms, yeah, yes, okay, have the same meaning? Clear, okay. Which of the following terms have the same meaning? Okay, so what are we having? We are having 1, far zone, 2, near zone, 3, Fresnel zone, 4, focal zone, 5, Fraunhofer zone, and 6, lateral zone. Okay. Now, is 1 and 2 the same? No. Since 1 and 2 is not the same, yes, okay, option A is out. Clear, okay? Is 1 and 4 the same? No. So option B, as in boy, is also out. Is 4 and 5 4 and 6 the same? 4 and 6. No. We haven't heard anything of that. It's called the lateral zone. So that's out. Is 2 and 3 the same? Do the near zone also go under the name Fresnel zone? Yes. Good. Is 5 and 1 the same? Is this and this far zone or Fraunhofer zone? Are they the same? Yes. So D as in donut, donkey, or Dumbo is the only one. Yes, okay, we are both 2 and 3 are the same, and 1 and 5 are the same. Did you guys get that?
Yes.
Good. Question number 307. Now, what is the point or location where a beam reaches its smallest dimension? Smallest dimension or smallest diameter. Or we can use as, okay, smallest area. What do we call that? That is called the focus. Yeah, okay. Please keep in mind, guys, this smallest point or smallest diameter, or the point, yes, okay, where it reaches there can also be referred to as the focal point. Did that make sense?
Yeah.
Okay. Penetration depth has nothing to do with that. Clear? Okay. Okay. Now, option D, which says that's okay, focal zone, could have been the right answer if it had said the middle of focal zone, because that's okay, right in the middle of your focal zone. What is it you have? Your focus or your focal point. But simply focal zone itself is not. Okay, because in the near zone, it's okay, the beam is still converging. Okay. Yeah, okay, in the far zone of the focal zone, yes, okay, that's where the beam starts to diverge. But in the middle of the focal zone, yes, okay, that's where we will have the beam as an arrow. So D could have been also been a right answer had it said the middle of the focal zone. Otherwise, that's okay, focus or focal point would have been the only answer. Did that make sense?
Yep.
Good. Good. Question number 3 is all of the following are true of the focus except. So we got 4 statements here. 3 of them is going to be true. 1 is going to be false regarding the focus. Clear? Okay. So statement 1 says it is at the end of the near zone. Guys, if this here is okay, was your beam. Now this is your near zone, and what do you have at the end of the near zone? Your focus. So A is true. It is the beginning of the Fraunhofer zone. Well, dear guys, this is your Fraunhofer zone. So it's at the beginning of the Fraunhofer zone. It has the highest spatial peak intensity. What did we say yesterday? At the focus, there's going to be okay where the beam mainly as okay will have the greatest intensity. Okay, but we even specified and says okay, it's going to be the greatest spatial intensity, because spatial intensity was okay related to your beam. Temporal intensity was related to your pulse. Did that make sense? Okay. Any questions? Good. Okay. Would it be correct to say that, okay, yes, the focus is at the start of the Fresnel zone? Well, okay, all this here is okay. Was your Fresnel zone, right? And do you have your focus at the start of the Fresnel zone? Is this what you call the focus? No. So D was a false statement when we talked about the focus. Clear? But if you think of, okay, the Fresnel zone being, yes, okay, another name for your far zone, yes, okay, then you may be thinking that way D would have been right. Okay? Did you guys get that?
Yes.
Good. Now here is going to, yes, okay, be a list of 9 statements, and they're asking us is this going to be true or false? But what we have it to begin with, okay, this is going to be a generalized statement that we say a PCT crystal in the shape of a disc produces a continuous sound wave, ultrasound wave, okay? The beam is unfocused, so we say it's okay. PCT is disc-shaped. Okay, okay, good. We have, okay, it's a continuous wave. Yeah, okay. And the beam is unfocused, or we can say it's okay, not focused. The following statements are either going to be true or false. So 309 says, the near zone is the only region where the beam of the diameter, okay, sorry. The near zone is the only region where the diameter of the sound beam is smaller than the transducer. Clear? Okay. Now, although SOK main and although SOK says not focused, but even SOK, we go and say here, even if this, for instance, okay, is your diameter of the beam, but you still see SOK that throughout the near zone, and we can say okay in some part of the far zone. Okay. I'd say it's okay, this and this doesn't come to the same. It's okay, the diameter of the beam is still narrower than that of your PCT. Okay. So it would be false to say that it's only going to be as okay in the near zone, that the beam's diameter is, what do you want to call that, narrower than the PCT. Did you guys get that?
Yeah.
Far zone. Oh, question, sorry. Question number 10. Or 310. The far zone is the only region where the beam diameter exceeds the diameter of the transducer. And that's true. Because if we take as okay the same beam here and says okay, because it's going to just okay keep on clear, okay. So as okay at some point, yes, okay, because like from here, let's say okay, and beyond, that's the beam is only going to be the region where we'll find that diameter of the beam greater than the diameter of the PCT. Okay, this PCT here will not be able to produce a beam that starts like this. Okay, so in the near zone, yes, okay, the diameter of the beam cannot be greater than the size of the PCT. Did that make sense?
Yeah.
Good. V11. If the diameter of the sound beam is 8 millimeters at a depth equal to twice the near zone length, then the PCT has a diameter of 18 millimeters. Now, pretty much okay, as a similar question as we had in last chapter, sorry, in our chapter review. And let's just try to draw it out and see. So what did, okay, let's, okay, then we have a PCT of 16 millimeters. okay? And okay, if the diameter of the beam is 8 millimeters at a depth which is equal to twice the focal or the near zone length. Now here it's okay, this is 1 near zone length. Clear? What happens to your beam here? Is going to be 8 millimeters. We have another near zone length. And what's going to happen here? The diameter is going to be 16 millimeters. Yeah, okay. But what they mainly say is if our PCG was 16 millimeters at a depth which is twice the focal zone, is the diameter going of the beam going to be 8 millimeters here? Is that what we have? Because this is twice your focal length, right? This is one focal length, and we can say, okay, this is another focal length. Did that make sense? So that makes it false. Did you guys get that?
Yeah.
Good. Question got it. What about the girls?
Yes.
Question number 312. The diameter of an acoustic beam produced by a crystal is 8 millimeters. At a depth twice the near focal zone or near zone length, then the PCG crystals is 8 millimeters. And what they mainly say is, okay, yes. Well, let's do this. They mainly says, okay, is this here going to be 8 millimeters? If the diameter of the beam at twice your focal length is 8 millimeters. What's going to happen here? It goes from 8 millimeters to 4 millimeters. But the main is, okay, just throw you around or toss you around by saying it's okay, twice the focal depth. If we say that, okay, let's just say that we have this focal depth here was 4 millimeters, then twice a focal depth, which is going to be, okay, a total of another 4 millimeters, which will make it a total of 8 millimeters, which is twice your focal depth. Okay, well, okay, the PCG is still, oh, sorry, the beam's diameter is still going to be 8 millimeters. Yeah. So what we had in our previous question where it became false, because they say, okay, the beam diameter is going to be that, then okay, but here it's the same. And the previous question they are giving us, this number says, okay, is that going to be the diameter of the beam at a depth twice the focal depth? If we had a PCT of 16 millimeters, that was false. And they say, okay, are we, in this case, we are going to have a diameter of the beam, which is going to be 8 millimeters. If our PCT was 8 millimeters, twice the focal depth. That becomes true. Did that make sense? So for questions like these, that's okay. You can say it's okay. The easy way to, that's okay, solve them is to draw it out. Okay, you don't have to make a Picasso and a Mona Lisa or something. Okay. Okay. It can be the crappiest drawing, but as long as you just go with, okay, with the numbers. Okay. Any question, guys?
Not yet.
Not yet. So that's not the question that you've been struggling with here?
No, it's coming real soon.
Okay, it's coming. Oh, sure. Okay. Oops, what kind of question is that going to be? Okay, my dear. 313. Now the near zone is the only zone, is the only region where the diameter of the cross-sectional beam decreases as depth increases. That is as true as it can be. Because, okay, what happens? That, okay, yes, in the near zone, what happens to the diameter of the beam? A decreasing diameter, right? Because it starts big and actually, it's okay, gets to its narrowest point. And that decreasing diameter is only happening in the near zone. Okay, where we can say, okay, in far zone, what's going to be the only thing that happens in the far zone? An increasing diameter. What do we call this increasing diameter? Divergence. What do we call this decreasing diameter? Convergence. Did that make sense? And it's even, yes, okay, true that we say, it's okay, that the diameter gets smaller and smaller and smaller as we go deeper and deeper and deeper. Did that make any sense?
Yep.
Good. $314. If the narrowest diameter of the beam sound, okay, let's see, it's okay. If the narrowest diameter of the sound beam is at a depth of 8 centimeters, then the PCT crystal is 16 centimeters. So they say, is it true to say that, okay, yes, our PCT is 18 millimeters if the narrowest point of our beam is 8 millimeters? That's true. Because what did we say that our diameter of the beam was going to be at the focus, which is the narrowest point? Because it says, okay, half of PCT's diameter. Okay, and the half of 16 is 8.
The book says false.
Hold on, hold
This
on.
is the one I was like,
Okay,
what
let's
the
see. If the narrowest diameter of the beam. Okay, hold on, because I misread it too. Sorry. Okay, let's see. If the narrow diameter of a sound beam is at a depth of 8 centimeters. Okay. See. At a depth of 8 centimeters. Then the PCT crystal's diameter is 16 centimeters. Sorry. That's not it. Because what they mean is that's okay. What that mean, what they asked, okay, you see, yes, okay. I misread it as too. They're talking about this depth here. I said, if this depth here is 8 centimeters, clear, okay. Before that's okay, the beam reaches to its narrowest point, which is the focal point. Is that because your PCT was 16 millimeters? Not necessarily. Did
why?
that make sense?
No.
Huh?
No.
Okay, listen. Look here, dear. Let's see. It's 14, right? Okay. If the narrowest diameter of a beam is at a depth of 8 centimeters.
But the narrowest point of the beam, is that not the oh geez, what's the name?
Okay, what do you call the narrowest point of the
The
beam?
focal point.
Okay, good. The focal
So
point.
if
Okay,
that's
listen.
at
No.
8,
But okay, the whole, there's one word that, okay, if you miss that one out, you may choose the wrong answer. And that is at. Because what it says is, if the narrowest diameter of a sound beam is at a depth of 8 centimeters. Did that make sense?
yep.
Good. That necessarily mean that, okay, yes, your PCT is going to be as, okay, 16 centimeters? No, it doesn't. Did that make sense?
Yeah.
Good. Okay, because, okay, this 16 centimeter PCT here, that's okay. Could have focused at a depth of, let's say, that's okay, 16 centimeters. It could have focused at a depth of 4 centimeters. It could have focused at a depth of 12 centimeters.
But isn't the narrowest point the focus point?
Okay, good. The narrowest point is the focal point, but that's not what they're asking here. And that's why I say, if you miss out the phrase, or I said, is at a depth of.
So can you give me how it would have to be worded? Like what would the correct wording be for this answer to be true?
Okay, you can say that's okay. If the narrowest point or if the narrowest diameter of a sound beam is 8 millimeters or 8 centimeters, then the PCT diameter is 16 centimeters.
Okay, so it's because it says it is at a depth.
Exactly. So here
So
what
if
they
it
made a
just
reference to
said
is
it-
the focal depth.
So it would have to say it is 8 centimeters.
Exactly. So if it said that, okay, yes, if it had been worded like this, I'd say yes, okay. If the beam at its narrowest point is 8 centimeters. Okay, then the size or diameter of PCT would have been 16 centimeters. Then it would have become true. Clear? Okay. But what they did here was that, okay, they say it's okay, at a depth of 8 centimeters, is that the depth at which the beam reaches its narrowest point? Does that necessarily mean that the PCT has to be 16 centimeters? No. Okay. And you saw it, okay, it didn't happen for me. That I first read the question wrong, right?
Yeah, it seems like a pretty silly question if you ask me.
Now, when you say silly question, what is it that you are striving for?
That I don't know. I just
I know what you're striving for, but don't even go there. Be honest, say what is it you're trying to convince me.
no, I just don't see the point of them making these questions worded so poorly to confuse us. Like, well, I just don't see the point in trying to confuse us is all.
Yeah, but here it's okay, and that's why I said there are questions that, okay, as you may have to read twice or thrice. Unfortunately, it's okay. It's not me who.
No, I know. I'm not mad
Okay.
at you. I just think it's silly, but all right, that's all. Thanks.
What I agree, let me put it this way, I agree. Why couldn't they just make it straightforward? But okay, yes. I guess not. Why is okay. And you can also say why. Call one thing under yes, okay, 3,000 different names. Why couldn't they just stick to one name, right? Okay. Yeah, okay. Now a lot of heads are nodding. It's okay, guys. Let's see. So question 315. So, the higher the frequency of an acoustic wave, the shorter is the length of the near zone. Okay, now please, guys, do not get thrown off by the term acoustic. Because, okay, that just means sound. Okay, so what they mainly say is, okay, the higher the frequency. Right, okay, the shorter the length of the near zone. That'll lead to a shorter length of the near zone, which we also said now the length of the near zone that's going to be equal to yes, okay, our focal length. Yeah. Okay. That's false because we know that frequency and focal length are directly proportional. So a higher frequency will lead to a greater focal length. a greater length of the near zone, not a shorter. Did that make sense?
Yeah.
Good. Question 316. The greater diameter of the transducer's piezoelectrical crystal, the longer is the near zone length. Says, okay, is the near zone length, also known as focal length, or equal to the focal length. Is that going to increase if we, for instance, okay, increase the diameter of the PCT? And we see that, okay, yes, they are directly proportional. So yes, okay, an increase in this will cause an increase in this.
Bless you.
Thank you, my dear. And that's true. We are at 27, 317. Now, the thicker the continuous wave transducer's piezoelectrical material or crystal is, the longer is the near zone. Thickness of PCT, is that directly proportional to the length of near zone? That's false. Why? Because this and this are not related. Simple as that. Should we go on? We can be done by 1 o'clock, and
Yes.
you have a weekend time.
Yes, let's do it. Let's get it
No
over
problem.
with.
I don't want you to rush through. If you don't get it, okay, please speak up. Don't say, okay, the more we keep our mouth shut, the sooner is that the mic is going to let us go.
Don't worry, Mike. I'll speak up.
Okay. If you need to grab a snack or something to, yes, okay, people to snack on, you are more than welcome to do so. So, okay, as what we have here is, okay, 4 disc-shaped PCTs producing continuous waves, which will, okay, yes, which design will create a beam with the shallowest focus. So maybe that's okay, just a different way of saying it's okay. Sorry. Lowest focal length or depth. Yeah, okay. And what do we have? It's okay, we have a large diameter and low frequency. We have a large diameter and high frequency. Then we have, okay, as a small diameter and a low frequency. And a low diameter and a lot. Okay, small diameter, high frequency. Yeah. Okay. So what are we looking for? The lowest frequency of lowest focal length, which we know is directly proportional to both diameter and frequency. Yeah, okay. So lowest focal depth and related, directly related, mean lesser diameter, lower frequency. So lesser diameter, lesser frequency, C as in cat. Break it up, Martina. Break it up. Clear? Now, question 19. All these crystals producing continuous sound wave, which design will create a beam with the deepest focus point. So yes, okay, guys, in the previous question, they just asked about the shallowest. Here they just go with the deepest focal point, and that's going to be greatest diameter, highest frequency. Clear? Okay. Because your focal length was directly proportional to both of these as well. Did you guys get that? So where did we have, yes, okay, greatest frequency and greatest diameter? B. Did that make sense?
Yeah.
Good.
Yep.
Good. 320. Two ultrasound systems are identical except from the diameter of the transducer's piezoelectrical material. Which of them, yes, okay, which system has the deepest focus? Now, what they say here is, okay, two ultrasound systems are identical except from the diameter. So that's okay, identical is going to mainly mean in this case here that the frequencies are the same, but the diameters are not the same. Okay, just yes, okay, make it, we can say it's okay, one is greater and one is lesser. Clear? Okay. Now, what the mean is asking us, okay, which produces the greatest or which has the deepest focus? So we can say, it's okay, deepest focus mainly means greatest focal depth, or we can say, it's okay, deepest focal point. Okay, all these here is okay, were directly related to both frequency, but which in this case, yes, okay, was the same. So, and directly related to the diameter of your transducer, which is going to be, yes, okay, will be the one with the greatest diameter, that will have the deepest focal point. Did that make sense?
Yes.
Good. Question number 21. Now, two systems are identical except from the frequency emitted. So what we mainly can say here is, okay, in this case is that the diameters of PCTs are the same. Okay, except for the P is okay, frequency emitted. So that's going to be that okay us that our frequencies will not be the same. Okay, and what they're asking us, okay, which system has the deeper focus? Okay, same thing that they're asking us, okay, deepest focus, or deeper focal depth, or deeper focal point, or whatsoever. Okay, which is directly proportional to, yes, okay, both of these. Now, since here our diameter are the same, okay, that's not going to affect it as such, but it's going to be the frequency where we can say, okay, now since they are not the same, we can say, okay, one is greater, one is a lesser frequency, and it's going to be the one with the greater frequency that has a greater, a deeper focal point. Had they asked about shallowest, then it had been this one here. Likewise, up here is okay, had asked about the shallowest, it would have been this one. Did you guys get that?
Yep.
Good.
Yeah.
So I guess there was only one question that, what's her name? Katie has a question about. Okay, so
Maybe.
we are, huh?
Maybe.
Maybe? Okay. Okay. So let's see, okay, question 322. Oh my God, why are you doing this to me? Up, 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 up. Now, as a sound travels deeply into the far zone, the beam diverges or spreads out. Okay, good. Which of the following will result in a minimum divergence of the beam in the far zone? Now we know that beam divergence was inversely proportional to frequency. It was inversely proportional to the diameter of your transducer. Now when they say is okay, minimum divergence, that's what they're asking us about. That's going to be the one with a higher frequency and the one with a greater diameter. Did that make sense?
Yep.
You had to ask the opposite, greater beam divergence, then there would have been lower frequency, lesser diameter. So since yes, okay, they asked that's okay, our option was going to be greater diameter, you can maybe exclude the two with lower diameter to begin with. Question number 323. Now, as the sound beam, as the sound travels deepest into the far zone, the beam diverges or spreads out, which results in the greatest. Okay, so we already answered that. Greater is going to be lowest frequency and lowest, smallest diameter of the PCT. Did you guys get that?
Yeah.
Good. So blue was 22, red is 23. Question 24. Now, two ultrasounds are identical except from the pulse repetition period. So A and B. Okay, so they are identical. So we can say, okay, diameter equals diameter. We can even say, okay, frequency equals frequency. Pulse repetition period is not equal to pulse repetition period. Which system has the deepest focus? Now, what they talk about here is deepest focus. What is the greatest focal depth? And that's going to be the same. Because they both have the same frequencies and diameters. Did that make sense? Or we
Yes.
can say your pulse repetition period is not related to the focal depth. So even if it was the same question with the same data and they had asked, okay, that's the smallest focal depth or shallowest focal depth, the answer would still have been the same. It's going to be the same for both systems. Yep. Even if we changed out PRP with PRF, the answer would have been the same. Did you guys get that?
Yeah.
So don't fall for that, okay. Well, that's because that's okay. This is not related to this.
Why do I not say that? What do you mean? Hi, Dad.
Okay.
I love how you
Marie,
What- where
325. Now, all of the following terms describe the shape of a sound wave created by a tiny fragment of a PCT, except from what we talked about today. Okay, so we call that a spherical wave. We call it a Huygens wavelet. We even call it as okay, V-shaped, or we can say okay, a V-shaped wavelet. Okay, but it's not going to be called an hourglass shaped, because that's going to be the shape of the beam. The beam is going to have that hourglass appearance due to these wavelets here is okay, constructively or destructively interfering with one another. If that makes sense.
Yes.
Good. Question number 326. Which of the following explains the difference in sound beam? Okay, in sound beam shapes. Sound beam shape created by disc-shaped crystals from that of a small chip of a PCT. Okay. And out of all these laws, that's okay. The one that we may not come across is going to be Morpheus' law. Okay. Huygens principle is the answer. Snell's law talks about diffraction, and Bernoulli's law is just another name for what we call the law of conservation of energy. Okay, bias, okay, where in this case, Bernoulli's law is going to be just talking about pressure and kinetic energy. Clear, okay. The last question. Huygens principle is based on refraction is wrong because that would have been Snell's law, right? Okay. Constructive indices. Well, okay, some of you may fall for as okay, constructive interference. That's not only what happens in Huygens principle. It also kind of talks about as okay, would be related to your destructive interference, right? Okay. Transverse waves. That is going to be as wrong as anything, right? Because sound waves are not transverse wave, right? What was a transverse wave?
Longitudinal.
No, my question is, my dear, what is a transverse wave? Okay, your sound wave is longitudinal, but what was a transverse wave? What do you mean by being a transverse wave? Yes, guys, I'm getting more and more difficult now. What did we mean by being a transverse wave?
The particles move perpendicular to the motion of the wave.
Okay, what does it mean to be perpendicular?
Not in the same direction.
Not in the same direction. Okay. So if I move this way and somebody move this way, that's transverse? No, okay, but it's not in the same direction, right?
It's through,
True?
right?
So if the particles move this way and the wave move this way, that's transverse. Or which is perpendicular, where you can say, okay, these two here, yes, okay, makes a 90-degree angle, right? Which you call a perpendicular angle, right? Clear? Okay. Interference. The whole bum bum bim bim boom boom of your Huygens principle is that it talks about interference of the wavelets, spherical waves, Huygens, Huygen wavelets, or V-shaped waves, right? Did that make sense? Now I enjoy an extra hour off or a delayed lunch break, if that's what you want to call it, or whatever, and Monday off. Now, if I was in your shoes, what I would use that extra day off to is prepare for my quiz. Okay? So if you have any questions, you can email them to me, or you can bring them up on Tuesday. Okay? Okay, guys. Now have a blessed and safe and joyous weekend, and see you guys on Tuesday.
Have a good weekend.
I'm trying to have it.
Bye.
Okay, thank you, Deb. All the best. God bless.